Exercise 83. Let's continue with filter find module. So we want to talk something related with Newton and Hodge numbers. So I will further reduce to explain this more explicitly. Here we just prove an exercise to prepare for that. So let D be a find module. We have recalled this in the last exercise over K0 such that finite dimension, and moreover we require this frobenius is bijective over this finite module D. We want to introduce an integer to D denoted by Tn of D called the Newton number of D. How do we do that? So the exercise for today is show that, so we start here, show that the following definition of TD, TND is well defined. So we're going to define this Newton number. We want to show this is well defined definition. If D is a phi n module over K0, actually we only work with very simplified case. We only work with dimension 1. Of dimension 1 such that dimension 1 means this is just a one-dimensional K0 vector space. Frobenius is bijective. Then we set Tn of D to be Vp of lambda, p-adic valuation of lambda. What is lambda? Where lambda is the GL1, which is K0 star, is the matrix of Frobenius under some fixed basis. And so to show it's well defined, actually we just want to check this is independent of choice of basis, right? So suppose we have another different basis. Let's say suppose D prime are two different base element, which means non-zero. And so phi d equals lambda d, and then phi d prime would just be phi of some c times d. Let me say non-zero. This is dimension 1, and so this is just phi of c and phi of d. And this is phi of c and then lambda times d. I mean, if you use d, then your t, your unit number is p-adic valuation of lambda. If you use this, then d prime is say d, and so d prime here is phi c lambda over c, and then d prime, right? And then if you use this, what you do is we p of phi c over c times lambda. And so basically the question is, are these two the same? So we claim that, or we have to do that, we p with c over c equals 0. It suffices to check that, right? But this is true because we know, sorry, this is for minutes. Because we know this Frobenius had the same valuation, p-adic valuation C. Okay, that's done. But why this is, let me say something more. This is because we are working with some local fields. So in particular, this is complete field. Actually already here. This is complete for the p-adic valuation. And so your Frobenius is giving a automorphism of K, let me say, automorphism of K0. Yeah. So you could define a different valuation just using Frobenius, and this again just give you extension valuation. And here you have VP. Here you could define way K0, and you could also define a way K0 prime defined to be way K0 of Frobenius of X. This is automorphism, and Frobenius fixed QP, and so it extends, again, extension of p-adic valuation. But this is complete and tells you there's a unique p-adic valuation. And so it's telling you that these two should be the same. Okay, this is basically the idea. Actually, more general statement would be, I think, for Galois group. Galois group of field extension of complete p-adic fields, of complete p-adic fields, complete local fields. Then the Galois group is continuous with respect to the p-adic topology, which means take any element from the extension, and then you apply the Galois action, then its valuation is not changed, because you give Galois action is possibly give you a different way to extend the valuation of the base field, but the base field is complete. It tells you that actually there's a unique valuation. This is a theorem. There's a unique valuation for complete field, and so all those Galois actions should preserve the valuation.